All right, so that's a selection sort algorithm, and it's a very simple in idea. You just keep going. You repeatedly find the smallest number and then put the next, because you want to arrange the numbers in your array from small to large. So you simply repeatedly find the smallest one and then put the next, okay? And that's to arrange them from small to large. Okay, but the time complexity of the previous selection sort algorithm, unfortunately, is not great. It takes quadratic running time, okay? So can we do better? And we can, and here is a much more efficient sorting algorithm called MergeSort, okay? And so the time complexity of this MergeSort algorithm, as we'll see later, is actually optimal, the worst case time complexity. What does it mean? It means that for the sorting problem, the lower bound, there's a lower bound, which is also the same time complexity as MergeSort algorithm. In other words, there's no other sorting algorithm can sort an array of arbitrary n numbers faster, asymptotically faster than the MergeSort algorithm. Okay, this is under a so-called comparison model, but let me not mention this later. Okay, all right. Another interesting thing about the MergeSort, so number one, what I'm saying is that number one, MergeSort has the, it kind of is the optimal algorithm, has the best time complexity, okay? Also, the idea behind the MergeSort, okay, it uses a so-called divide and conquer mechanism to solve problems, okay? This is a very powerful paradigm to design algorithms, okay? And also often, this divide and conquer paradigm leads naturally to recursive algorithms. So we're going to see recurrences again later and how to solve them. Okay. So what's the idea here? What is this divide and conquer? Well, so this is the, let's say this is an array of numbers that we wish to solve, to sort. Okay, I have n numbers inside. Okay, so to sort that, I'm going to do the following. I say, okay, let me actually first divide it into two portions, okay? Let's say that's the left portion and the right portion. So this is the left portion, this is the right portion, okay? Then what I'm going to do is that I'm going to sort each of them individually. So I now divide them into two parts. Now I sorted this one, so the pink color is the sorted portion of the for the left portion, and I also sort the right part. So this now also becomes sorted. So pink means that now they're sorted, okay? Now I have two sorted subarray, and in the end, I put them together. I put them together into a single, merge them into a single sorted array, okay? And then return. So this is the idea, okay? So instead of directly sort the entire thing, I'm first splitting them into two subproblems, smaller subproblem, and then sort each of the subproblem and then merge the solution together, okay? Why is it called divide and conquer? Well, this is the divide step, okay? Where instead of the entire array, you first divide it into smaller subproblems, okay? And now this is the conquer step, where after you solve this for the subproblems, okay, you kind of conquer, you merge the solution together to get a valid solution for your final problem, okay? So this is called divide and conquer, okay? Well, but this is a high-level idea, but how exactly are we going to implement this idea, okay? For that, we need to decide first, how are we going to divide? Well, there we just do something simple. You're giving me an array of size n. I'm just going to cut it in the middle, okay? And then divide it into the left portion, left half, and the right half. So that's how we're going to do divide for this specific one, okay? But then we said that after that, we are solving each of the subproblem, right? We have to decide, how am I going to solve this subproblem? How am I going to sort this half of the array? Okay, how do we do that? Okay, so this is a step we need to describe, okay? And after you have the two sorted subarrays, we also need to describe the last merging step. How are you going to, given two sorted subarray, how are you going to merge them into a single solution, which is a sorted array for the entire original array? Okay, so these are the two steps we need to specify in order to have this complete algorithm. Okay, so let's first look at this how we solve the subproblem. So, well, we already have, so instead of big problem, we now have a subproblem. Let's say this one, okay? To sort that, let's call the whole algorithm, let's call it MergeSort. This whole framework, okay? The idea is that, okay, to sort the subarray, I can apply the same strategy again. In other words, inside, I can again split that into half and then split them into two halves and solve the subproblems and then break them down and then solve them independently and then merge the solution. Okay, so I can apply the same strategy again. In other words, for this step, I could apply this same algorithm recursively, but on a smaller portion, only on the right side, and on here is only on the left side. Okay, so the idea is that we're going to apply the same idea. That's what we're going to do. Okay, so this is how we're going to solve the subproblem. Okay, but I still need to tell you how we now do the conquer step. Okay, so for that, let's first assume that it can be done by a procedure called merge. Okay, then here is a complete algorithm. What do we have? Well, first, the first line basically says that if L, so what we're going to do is that this algorithm is going to apply, so this algorithm is going to apply this merge sort idea to the portion of the array from L to R, a subportion of the array. Okay, so for example, we're going to see it in a minute. Okay, so you only every time you only sort a subportion of this array. Okay, all right. Now the first line basically says that if this subportion become of size only 1 or even 0, what does it mean? If it's only size 1, that means that I don't need to do any sorting. I'm done. So this is the base case. This is where how the algorithm, you cannot keep cutting, divide them into halves. At some point, you have to stop. You stop when the size become either 1 or 0. Okay, basically now you know the answer because if it has only one element, it's already sorted. Okay, and then here, what we do is that then now we're cutting the array by in the middle, right? So I need to know the index of the middle. Okay, so mid is basically computing the so you have a subarray. This is your A, and this is L. This is R, and right now you're solving the portion between L to R. Okay, so the first step is that we need to compute where's the middle. Okay, we compute the middle, so that's what this line is doing. Okay, we find the middle. Then we divide it into two portions. The left portion is from the beginning, the index 1, to the middle. That's the left portion. I sort this portion now recursively using the same algorithm, merge sort. Okay, then you now sort the right portion from mid plus 1 to the right. Then you sort the right portion also recursively using the same algorithm. Okay, and after that, you use another procedure. So after that, note that A1 and A2, after that, it's not A1, A2, I should let me write it more precisely. It should be, after that, the left portion and the right portion are already sorted. Then you merge them into a single sorted array B. And then you return B. So this is the conquer step, okay? So after you sort the green portion and after you sort the blue portion, you use the merge procedure to merge them into a single sorted portion, okay? And then you return that, that's it. Okay, so this is what we have. All right, and as we can see that this is a recursive algorithm because we call the same algorithm recursively but on smaller problem. Okay, so in general, how does it work? Well, suppose I'm given the array A that I want to sort. The first step is that I'm going to call MergeSort A1n. Okay, now inside this algorithm, what happens? Inside this algorithm, I'm going to split in the middle and then recursively call MergeSort A. It should actually be 0 to n minus 1. Then from 0, the left, the beginning, to the middle, which is n over 2. And then here, I'm going to do MergeSort from the middle to the end, right? So this is what we do, okay? So basically, we cut it in the middle. And then to solve this, what happens? Well, inside this, we again do the same. We're going to, inside this execution of this call, we're going to again cut it in the middle, split in the middle. And then first call the left half. Now it's going to be into the fourth. And then also the right half. Same here. Within this right portion, if you the algorithm will then recursively cut it in the middle, which means that we're going to then call MergeSort A n over 2 plus 1 to 3 n over 4. And then that's basically the left portion of the previous right portion, and then also the left portion. Okay, and so on. So the algorithm would recursively keep splitting and keep doing this till in the end. When do we stop? We stop when we meet the termination. When the subarray, you keep cutting until the subarray that you're going to call your MergeSort on become now only of length 1 or 0. That means that we don't need to cut anymore because this is already sorted. Okay, so then we return. When you return, let's say that right now, when we return, let's say that we now returned up to this level. We returned this one. If this one run successfully, then after that, we get a subarray, which is the sorted portion of the first quarter, okay? And then here we get a sorted subarray of the second quarter. And then this merge procedure will then merge these two to give us a sorted subarray of the first half. Okay, the same on this side. Okay, so after we get the sorted second half, this two, when we perform merge, that would return, give us a merge the entire sorted array of the entire array. Okay, so this is how the algorithm works. First, we keep splitting till the bottom, then we come bottom up, come back, at which point we assemble the solution piece by piece together, and then in the end, we get the entire array sorted. Okay, so that's how the algorithm works. All right. Okay, so this is recursive call, and I do want to point out that this algorithm is not in-place sorting, because what happens is that at this step, okay, and in fact here, as you can see that when we merge two subarray, okay, we now open a new subarray B, okay, to store the sorted portion, version of the those. So basically, you start with two subarrays that's already sorted. Okay, this is left A and the right A, and then you merge them into a single one B. And to do this, we open a new array. We're not using the previous subarray, that space. Okay, so it's not in place anymore. We have to allocate a new array for that. Okay. And well, you may say that why is it so important to have in-place sorting? Well, it's not necessarily important, but having an in-place sorting means that your algorithm, space speaking, is also very economical, because other than the original array, you're not using any real extra space. Okay, so in terms of memory access, this is more economical. Okay. All right. Correctness. Okay. Now, remember that we've seen this last time. Okay. To show that a recursive algorithm is correct, what we want to do is that essentially 3 steps, this inductive idea. We make sure the algorithm works for the base case. Okay. Then we make sure that the recursive calls are on smaller problems and the algorithm indeed terminates. Namely, there are termination conditions, so you don't just keep going on forever. Okay. And the last one is the inductive step. Remember, this is basically the inductive step. Basically, within one recursive call, if you assume that the lower recursive calls all work, then the current algorithm also work. Okay, so that's the inductive step. And if we can convince ourselves of these 3 steps, then we can convince ourselves that the algorithm is correct. Okay, so let's see that what does it mean for this merge sort algorithm. What's a base case? The base case is basically you don't have any more recursive calls. Okay, in our algorithm, that basically means that we stop here. Okay, because in this case, we don't do anything. In other words, the base case is 1, the size of the current portion of this array that we're going to inspect is of size at most 1. Okay, of course, the base case is correct because obviously, if you have only 1 number, that's always sorted. Okay, so this base case is done. Okay, the second step is that does this recursive call always breaking into smaller subproblems? Does it terminate? Okay, well, again, as I showed you previously in that tree example, we keep each time we reduce the size into problem of size only half of the previous size. So the size keep decreasing very fast. Okay, and it does terminate because as you keep decreasing, at some point, the size will be either 0 or 1, which is handled in the base case. So it does terminate. Okay, so the second this step is also fine, no problem. Okay, the last one, which is usually the harder one to convince, is the inductive step. Okay, namely, if the recursive calls return correct output in your algorithm, that's at the current level, your algorithm returns correct output. Okay, in other words, what this says is that if you look at this algorithm, if we're saying that if this out is correct and this is also correct, then does this algorithm give us a correct output? That's what we're asking. Okay, so we ask, does this implies the correctness of the entire algorithm? So if the recursive calls are right, does this imply the whole algorithm is right? Okay, well, this is essentially our idea. We said that if your left half are all sorted, okay, so this is the left, and if your right half are also sorted, and now, well, we haven't really described this merge step, but if the merge indeed merge them correctly into a sorted array, then obviously in the output is correct. So the inductive step is correct as long as our merge step is correct. Okay, so what I said is that yes, as long as that this merge procedure is correct, as long as merge can indeed merge to sort the subarray into a single sorted array, then we're done. Okay, so in other words, the only thing left for me to describe to you is how we implement this merge step. Namely, we are already given to note that this is a sorted subarray B and C. Okay, like in this example, each of the column are one of this subarray. Each of them is already sorted, and I want to merge them together into a single sorted array. Okay, so how do we do that? Well, we have to leverage the fact that B and C, each of the subarray, are already sorted. Okay, in particular, the way we think is the following. Let's say that I want to merge them into a single sorted array. What is the first number? That should appear? What should be the first number in the merged sorted array? Well, that one has to come from the smaller of this smallest number in each of the individual array. In other words, the smallest number of the entire merged array has to be the smaller of smaller of 2 and 3, right? Because each of them is smaller in their individual array. So in other words, the first number we're going to have, in this case, 2 is smaller than 3. So the first number we're going to have is 2. So I'm taking this, I'll put it into a new array. I put 2 as its first. Now I ask, what is the next smallest? Well, now the next smallest will be the smallest in the first array and the smallest in the second array among the portion we have not yet output. So 2 is already output. So now I'm comparing 3 and 4. So I have the pointer here to indicate the portion I have not yet finished the processing. Okay, so next the smallest one will be the smaller of these two numbers pointed by the pointer, 3 or 4. So 3 now is smaller. So I take 3 and this pointer also move up. Then what's the next smallest one? That must be between 4 or 8 because these are the smallest in each individual array. So the smaller of the merged array has to be coming from this 2. So the next one has to be 4. Okay, then we'll again compare 5 and 8, and the 5 is smaller. So that means the next smallest number in the merged array is 5. And the 7, now 7 is still smaller than 8, and that means the next smallest one is 7. And after that, the first one of the arrays is already empty, so the remainder would just be 8, 10, and 16. So this is the entire procedure, how we merge them into a single sorted array. Okay, so essentially, again, on the high level, what are we doing? We know each of the subarrays is already sorted. So within them, the relative order we already know. Okay, so to know that what to output for the merged array, we just kind of compare the at any moment compare the smallest of each of the individual array. And that's basically we can just since they're already sorted, we can just move up one by one. Okay, so use a pointer to indicate that. All right, so here is the pseudocode of the procedure that I just described. Okay, let NB and C denote the length of this two subarray B and C. Okay, and this means that the length of the output array. So we're going to merge B and C into a single array of size NO. Okay, and initially the output array, we initialize it to be an array of size NO. Okay, and what this for loop is doing is basically we're just looking at we're basically using those 2 pointers. Always compare the current smallest number of the portion we have not yet processed and take the smallest to output for the merged array. Okay, so the merged array just keep retrieving what's the smallest of the remaining numbers we have not yet processed. Okay, and at any moment, if so I have 2 array B and C. And let's say that this is here, this is where the IDB is. And let's say this is where IDC is. Whatever below them, we have already output, already processed, already output in the output array. Now we need to know that for the remainder, this wide portion, who is the smallest? Since each of them are already sorted, the smallest has to come from here or here. In other words, I just need to compare these 2 numbers. Okay, so if this number BIDB is bigger than this one, that means that the smallest one is the one stored in here. Let's say, for example, if this is 10, this is 4, then clearly the smaller one is the one stored at the CIDC, and that's what we do. We output this number to the merged array, and meanwhile we increment this IDC by 1. We move this up because this one is also already output processed. Okay, so we move this up by 1 and we repeat. That's it. Okay, this is in the code because that maybe one of them at some point got completely finished. Okay, you already finished processing it. Okay, this is just saying that if IDB is already bigger than the length of array B, that means that I already finished. So the IDB is already here. I already finished the processing entire array B. All the numbers are already output. So in this case, I don't need to do it here anymore. I just need to process only the remainder numbers in C. Okay, so this is the entire algorithm, right? All right. The time complexity, as we can see, we only have a for loop where the for loop only runs in NO iteration, where NO is the total size of the 2 input array. Okay, and within the for loop, it only takes constant time. As such, the time complexity of this algorithm takes time of the total size of the input subarray. Okay, the size of NB, length of B and the length of C. That's it. Okay. All right. So this finished the description of the entire algorithm and its correctness. Okay. This is so conceptually, MergeSort is a very simple algorithm. You just every time cut it by half, and then solve the left part and the right part recursively. Solve this and this recursively, and then use the merge procedure we just described, merging the solution together into a single sorted array. Okay. All right. So let's now look at the time complexity of this algorithm. Okay. Well, as before, for the time complexity, we say, okay, let's use T of n to represent the worst case time complexity of this algorithm performed over a portion of the array of size n. Okay, so we want to figure out what this T of n is. Well, we look at this algorithm line by line. This line takes constant time. This also takes constant time. Okay, this one, how much time does this line take? Well, here, this one is calling the same algorithm again, but on a smaller portion of the array, which is only from the left half. Okay. In other words, if currently the portion of the array we're looking at has size n, then for this subroutine, we're only calling the same algorithm on a subarray of size n over 2. Okay. And the time, we don't exactly know the time, but we know that we already used t to represent. So the time for this is at most t of n over 2, because we're now running the same algorithm on an array of size only n over 2, half size. Same for this portion. Okay, so here we're now running the same algorithm on the right portion, which means that the size, if originally the size is n, now we're running it on a subarray of size n over 2. So this time, the worst case complexity is simply t of n over 2, because that represents what is the worst case time complexity of MergeSort algorithm performed on a subarray of size n over 2. Okay, and this merge procedure, we just said, the merge procedure takes time, which is proportional to the sum of the size of the input 2 subarray. Each of this input subarray is of size n over 2. So the merge takes time Cn. Okay, so put all of this together, this is still dominated by linear. We write that the time complexity of our algorithm is basically t of n over 2 plus t of n over 2 plus Cn, which is 2t n over 2, here means plus Cn. So this is the recursive call on left half. And this is the recursive call on the right half of your subarray. Okay, and of course, in fact, we also have the termination. So the termination is basically when the size become 1, we know that that only takes constant time. Okay, so the right way to write the recurrence, putting them together, is that t of n equals 2 t of n over 2 plus Cm of constant. So this is our, we didn't get the time complexity yet, but we get a recursive relation for the time complexity function T of n. Okay, so that's the recursive relation. Okay, all right. As we said last time, when we look at the binary search, this is not yet there. We still have to solve this recurrence relation in order to know precisely what's the formula for the time complexity. Okay, and that's what we're going to do next. Okay, we're going to look at how to solve this recurrence relation. Now I'm going to skip the termination here with the understanding that T of constant is constant, T of the, I didn't write it here, okay? All right, so how do we solve this recursive relation? If you remember last time we said one way to do this is that you basically keep unrolling this, because I mean recursive relation, you can then apply the same recursive relation on the smaller subproblem, and you unroll it for a few times and see whether you can get a pattern or not. Okay, and after you get a pattern, you write a general formula for the case unroll and figure out when does this unrolling, this keep expanding, terminates, when does it finish, when do you when can you stop doing this unrolling. Okay, and then you figure out the number of iterations of the unrolling needed to reach the base case. Then you plug in that number into the general formula to get to the total time complexity of T of n. Okay. All right, so let's look at it more precisely. What does this mean? Well, remember that what this says is that basically we know that T of some size equal to, the relation is that no matter what this is, this equal to 2 times T of the problem of size only half. But then here, C times the size, okay? So this can be any number, okay, this star, okay? All right. So let's see, what do we have? We have that T of n equal to 2T of n over 2 plus Cn. Now, this is good. This is just some number that we can report, but this is not good because we don't know what is T of n over 2. That's what we are trying to find out, okay? But I know that I can apply the same formula to T of n over 2. And when I apply the 2T of n over 2, I get T of n over 2 should be equal to 2 times, then inside the size need to divide by half. So my size right now is n over 2, divided by another half is n over 4, plus C times the current size. The current size here is n over 2. So this is just apply the recurrence relation to T of n over 2. Okay? And this, if I write it out, take it out of the parentheses, this give me 4T of n over 4 plus C n over 2 plus Cn. This is after the first step of expansion, okay, of this unrolling, okay? Now, we don't like this T of n over 4. We want to do this unrolling again. So we say that, okay, inside, actually, let me use a different color for this, so that you see the relation. T of n over 4 equal to, using the same formula, that's twice T of, the size has to cut by another half now, that's n over 8 now, n over 4 divided by 2 is n over 8. And then plus C times the current size, which is C times n over 4. Oops, I made a mistake here. So here, when I take this one out, it's n over 2 multiplied by 2. So this 2 disappears. So here I wrote it wrong. Okay. All right. So now I apply the same recurrence to T of n over 4. And then outside, I have this from the previous iteration. That's 2Cn from the previous iteration. Okay. Now again, let me take this out of the parentheses. 4 times 2 is 8. And inside is 8. And then 4 times n over 4. 4 cancel. I get Cn plus this 2Cn from before. Okay. Or in other words, now I get 3Cn. Okay. Now, if we still don't see the pattern, we can do it one more time, and you would see that when I do it one more time, what happens? Okay. Now, each time when I apply this formula, inside the size of the problem get cut by yet another factor of 2. Okay, so from 8 now it becomes 16. But the number of problems outside, I have to multiply by a factor of 2. So right now I have 8 multiplied by a factor of 2, that's 16. Okay, and then outside, before I had 3 times Cn, but then there's going to be another one coming out from this part. So it's going to be 3Cn plus another Cn. So outside, I'm going to add yet another Cn, which means that now it's 4Cn. Okay, so now what you notice is that essentially what we're saying that call this one is the first iteration. Okay, then at the case iteration, what do we have? Basically, every time when we unroll it once, okay, inside the size of the variable, the problem, the size cut by half. So you start with n, and every time the problem size cut by half after k times is n over 2 times 2 times 2 k times, which is 2 to the k, because every time you would divide by another factor of 2 here for this within t, which is the size of the problem you're looking at. Okay, and outside, what happens? Every time you expand outside, you multiply this by a factor of 2. Okay, that means that outside you have 2 to the k. Okay, and what do you have here? Every time you just add another factor of Cn. Not add another factor, you just add another additive term, which is Cn, every time you expand this. So you see, the first time I have Cn, then it's 2Cn, then it's 3Cn, and so on. So after k times, I have k. This is what we have, the general pattern. Okay, and now the question is that when does this process stop? When can we stop? Okay, it stops when we don't need to do recursive call anymore. When we get to something which we know what that is, that means that when n over 2 to the k equal to 1, that means that k equal to log n base 2. Because when this happens, we have 2 to the k t of 1 plus cnk. Okay, and the k is log n base 2. Now 2 to the k, as we see, equal to n. So this also means 2 to the k equal to n. That means we have n okay, 2 to the k equal to n both, because here, or if you just plug in the k equal to log n base 2, 2 to the power of log n base 2 is n, okay? So, and now we can stop because we know what is t of n. We know that this is constant, this is our termination. That's why we don't stop when it's t of n over 2, because we still don't know what is t of n over 2. But when it finally comes to t of 1, we know we can, now that's just a constant. Okay, so we don't have to unroll anymore. Now this unknown becomes something that we know what that is bounded by a constant. So now this is basically a linear factor, and this is n log n. As such, the n log n dominates. So we have time complexity is n log n. Okay, so this is the entire duration. Okay. All right. So this is what we what I just wrote, and here is the same thing written here that gives us the time complexity n log n. All right. Okay. So that means that the sorting problem, we give you an algorithm to show that the sorting problem can be solved in n log n worst case time complexity. Okay, and it turned out that this is optimal. Okay, if you assume the so-called comparison model, which eventually means that your machine, in order to know who's bigger and to number who's bigger, who's smaller, the only way that you can get information, you have to compare the two numbers. Okay, so if under this assumption, this algorithm has optimal time complexity, means that you cannot find an asymptotically faster algorithm than MergeSort for sorting the arbitrary array of elements. Okay, all right. But as I point out, the algorithm is not in place, which means that as you keep doing the recursive call, in the middle, you have to repeatedly open a lot of subarrays and so on, which has, even though asymptotically, the memory footprint is still linear, but then it uses a lot of extra memory compared to in-place sorting, okay? So in practice, merge sort is not necessarily the popular approach, despite that conceptually it's very simple. In practice, actually, quick sort tend to be more popular in many of the packages and so on for sorting. We're going to talk about quick sort in 2 lectures, okay? All right, so that's what I want to say about the